Okay, good morning, everyone. Okay, I'm going to talk about composable machine learning this morning. This is a work that my team and myself has been doing for the past several years. And before I start, I want to acknowledge some of the key people contributing to this talk. That picture over there is Zhiting, who is actually the author of the software package I'm going to present today. And then Qirong is a co-founder of my company, Petuum, and he also helped creating the slide deck. And of course, my R&D team in Petuum and my research team of Sailing Lab at Carnegie Mellon made a great deal of contribution to the basic foundations of the talk I'm going to give. All right, so this talk is about how to make AI happen, in real world for various applications. Let's begin by asking the question about what do you think about AI right now and what it's supposed to be doing, in your daily life. So here's a snapshot of some of the possible expectations or imaginations that AI had for people had for AI. They do, for example, very fancy applications in autonomous driving, in robotics, and they probably sometimes can perform superhumanly, in games like chess and Go and so on, right? So these are a aspect of AI, which is very inspirational, but in terms of application, it is either too far to be practical, or it is not actually quite practical. For example, the game, it's like a smarter calculator. That is, we know that they're going to beat human, but so what, right? The other type of applications, which seems to be connecting better to our daily needs, are like this. Computer vision applications for recognizing objects, machine translation, so that you can travel to foreign countries without a translator, and maybe discovering secrets in DNA so that we can diagnose your disease and so forth. So these are problems which may be of a more practical value, but we ask, is current AI or future AI well positioned for that problems or not? Well, I share with you the following, that we, as a company and I as a researcher have been working a lot, in application areas of AI. And we find that real world AI problems, especially put it into a real world context, is really difficult. For example, here is a problem that we recently worked on, which is to help the cement industry improve their production and their energy emissions and so forth. And what is, first of all, in order to even be in the playground, to be in the game, you have to know this industry really well. And that's basically what the industry is doing. They need to basically start from getting the raw materials ready for all steps of production. And then you need to go through a process called the pyro process, which includes a lot of things like grinding the material, heat it up, adding different type of materials, control the temperature, while not hopefully generating too much pollution, and also save energy and so forth. And at the end of the day, you will have a massive amount of production. You package it, dispatch it, and sell it to the clients. This whole process actually had a lot of room to improve, and this whole process is now mostly manned by human. And these are the goals they want to achieve, to improve, for example, the fuel efficiency, to reduce the waste emission, and so on. And how a human being is actually doing it? Well, in order to even make the improvements possible, you have to understand the whole status and the states of this production process at any time. And that means you need to mount many IoT sensors, to this whole process, in production line, which involves assets, process, factories, corporations at all different levels. And even for a small amount of application optimization, say we want to improve the performance of a cooler. Typically, it involves the reading out of a few thousand sensor signals, and then a poor guy has to sit in front of a massive panel, a dashboard, looking at all these dials, and then hopefully make a judgment about what to do, what should we do, in the next movement. If you want to go a little bit bigger, say kiln optimization, and you need to deal with very typically 20,000 such signals. That actually signal is coming every second, by the way. It's very, very high frequency. This is already bigger than the Dow Jones, the stock market index, basically. And in fact, if you move out of the cement and into, say, steel and oil refining industry, you again, can see, maybe 10 times more than this, because their equipments are simply more complex, okay, and more expensive. Therefore, we are talking about, a few 100,000 signals and so forth. And making optimizations, in such a very high-dimensional space is very, very difficult, if possible, for a human being. And now people are looking for AI. Those executives in these companies are really having high hope for AI. They thought we can just ship out a magical software, such as a Microsoft Word, Office type of software, and they mount it, and then suddenly you can, remove the people and see the whole thing being automated. Well, this is a very, very nice kind of a vision, but on the other hand, obviously a very high expectation for we as the developer, because the truth is that automating such a factory is way more complex even than self-driving a car, or autonomously driving a car. So how can we make some progress? Well, that involves many steps. You need to have the methodology and the tools to process the data, from raw signal. You need to develop algorithms for making predictions and generating controls. And then you need to also mount and deploy it into their factory environment. It's not going to be in the cloud in many cases. And then they need to run 24/7 with very little maintenance or no maintenance. And this whole thing, is not going to be solvable by the typical cargo game type of playing or downloading some software or some algorithm from a algorithm marketplace, and suddenly get the whole thing work. And I show you already here some fragment of our software architect underlying the solution we are providing. It is massive. It is very, very complicated. Imagine writing the code by a developer for this kind of application. I'll tell you, it can be very difficult without the kind of tools we are using in our company. Another example, probably more familiar to you, maybe cement is too remote to you, but healthcare is very close. You go to hospitals very often, I guess. And typically in a hospital, you are going to be, well, unfortunately, in the God forbidden, if we are in an emergency, we may be in one of these rooms. And then you will be measured by many, many devices. And they create, again, a large amount of signals. And in fact, this is a picture I literally got from a friend of mine who happened to be a pediatrician. Okay, and he took this picture and he pointed to me that that little patient is right there. It's very tiny compared to this massive array of equipments that is used to generate the data. And then imagine that the doctor, at least we believe or we hope that the doctor is going to use all this data to give you a diagnosis or maybe give you a prescription. The truth is that this didn't happen. In fact, if you ask doctor, do they actually consume all this data and make their decision accordingly? If they're very honest, they will tell you they cannot do that possibly, right? Again, this is a very typical healthcare problem, which is different from what we saw in high-profile publications such as Nature and Science, where people are downloading or developing a massive deep learning model, making a tagging or a labeling of a cancer image, and calling the performance to be better than a doctor. Okay, a diagnosis is way more than just diagnosing or labeling an image. It at least should produce something that is actionable. For example, here we were asked to produce a discharge report of a patient based on the radiology pictures and also clinical notes and so on. And this whole process has to be also integrated into the doctor's workflow. And that means simply having an algorithm that labels an image is going to be way less adequate. And what you really need is this full pipeline of solutions which understand the image, understands the text, and then accordingly generate digestible, human comprehensible descriptions and reports, and then they can go get discharged or get billed and so forth. And likewise, it is not going to be a single program. It's going to be a very complex program that contains many components. Again, you don't get it from an algorithm marketplace, and you don't get it by people who can only do cargo game computations. And how people get there at this point? I guess even including myself or my colleagues inside the university and many of my colleagues in those big companies, the way to get nowadays an AI solution is mostly by crafting. Okay, you assemble a team of experts and they do some research or they read some papers and then they do some innovation and then they put things together, tuning, tweaking, and maybe trying on different data sets and so forth. And then they roll out something, which in my opinion is a craft. It's not really a production. Why? Because if the second time you ask the same team or the second team to do the same thing again, you will get something different. It's not repeatable. Okay? And also if the condition changed, most likely the whole thing has to be redone rather than being reused. So how can we really move AI into a discipline or a process, which is like aviation industry or even civil engineering industry, where people can use process, use repeatable building blocks and reusable building blocks and assemble things in a principled and systematic way. So that's the question I ask. It's not just a research problem, it is actually a very critical, economically sensible engineering problem. So that leads to the talk. Okay, here's the outline. I'm going to share with you a modern, maybe a aggressive view of machine learning, not seen very often by nowadays researchers who keep building fancier and fancier models. We're going to decompose or dissect machine learning as an area, okay, into based on first principle, into building blocks and components, and see what they are and how they come together to produce solutions. And then we are going to show you how we can actually build a tool, which we call Texar here, to allow people compose complex, non-trivial solutions based on these building blocks, using proper rules and convenient interface, hopefully. And of course, I'm going to say a few words about how to make it production ready in terms of scalability and generalizability. Okay, so the first part is the concept about composable machine learning. Again, I don't know the background of the audience in this room. I wonder whether you are mostly developers or you are executives and all that. But I guess one question we ask is why bother? After all, we do have tremendous progress in the past decade in machine learning, in deep learning, where more and more powerful models has been rolled out. Right, starting from several years ago, the AlexNets and the ResNets, which are doing really very, very competent image classification type of applications. Now to AlphaGo, which is as powerful and more powerful than the best Go players in the world. And these days we are talking about transformers and birds, doing very effective natural language processing type of applications. And the most latest model called the GPT-2 is already used for some language generation task. And a common kind of trend underlying this model is that the model is getting more and more sophisticated and bigger to the point that this latest model is already having 1.5 billion number of parameters. Imagine that this is almost like a big pond, collecting knowledge. Even to fuel the knowledge there, not alone blend it and generate creations and insights, how much data you need to train them. That's actually one of the bigger bottlenecks already. But even if they are trainable, okay, with both data and also infrastructure and hardware, are they really good enough to solve the kind of problems I just mentioned? Should we expect, for example, we have a black box made of a magical, monolithic, big model where you can dump in data and get a solution out of it automatically under the name of so-called auto ML? Well, I'm not a believer of that, to be honest, because we tried quite a few times and they didn't work. And let's maybe just scratch the surface of why it didn't work and why we shouldn't even expect it should work, right? Well, there are a number of difficulties, in dealing with these single giant models. Obviously, it is very hard to explain all these models. Typically, there are some magic tricks, okay, some miracles that we hope to happen in somewhere in this model, and that usually requires a great deal of expertise, domain knowledge, in order to be designed, and therefore the key will hold in maybe just a few people, if ever the key ever exists, right? And then, of course, if the model is built in that way with black box and miracles and magicals inside, then when something didn't go very well, debugging it, especially not by the creator, and maintaining it, by staff, can be very difficult if possible, right? And also upgrading the model is very, very challenging because, the peripherals, the environment can change. For example, what if in some day we're not anymore using JPEG, we're using a new encoding scheme, a coding scheme for images or text. What do you do with the models? Are you going to just reprogram the model, or you can just plug in, a certain module inside the model, which could handle a new data format, but leave the rest of the model unchanged? As of now, it is not possible in most of the cases. And of course, scalability and other things become a real issue because these models are getting bigger and bigger every day. And in our own experience, inside Petuum, where we work with real-world customers on real-world problems such as cement production, such as healthcare, and we found those big models aimed for a specific task is inadequate. And instead of using all these complex examples to explain, where and how, the composable machine learning concepts and the practice can be put into play, I'm going to introduce a much simpler running example, which is known as the machine translation, where you want to translate, the text from one language to the other language. Even for a task like this, it is already, not feasible for very big model to address. It includes many of the components, such as handling the data, of all different formats and different level of noises, to the point of designing the right model, and then how to train it based on different criteria and different needs. And if you really are hoping to write the solution from scratch, it usually results in tens of thousands of lines of code if you can already build it, and then talking about maintaining, upgrading, and debugging it is creating a very, very big overhead. So that brings us to the solution that I would love to share with you, which we call composable machine learning. We want to first build a very, very systematic representation of components and the knowledge and also the process in the machine learning creation, so that with this you have a very modularized way of building complex applications like you do with Lego. You have all these different building blocks which can be assembled and plugged and modulated, adjusted based on needs. So to sum up, we want to build AI solution more easily with this possibility of pick and choose from a library of Lego components, and you hopefully can walk away from this boilerplate where you write one-off code on and on based on different applications. Okay. So how to achieve that? So every developer who have ever built a machine learning real application, not by downloading a piece of algorithm, but by building it from scratch, probably had that experience. You need to first digest, pages and pages of equations and maybe formulas and all sorts of tricks. Right? If you stay at that level, it's impossible to get systematic because next time you need to read the whole thing again. So thanks to the mathematical first principles people use to create all these different machine learning innovations, in fact, beneath all these equations, there indeed exist very systematic structures of those knowledges. For example, because I'm a professor, I need to teach machine learning to students. We usually summarize different aspects of machine learning using all these different components, such as a loss function, for you to guide the training of machine learning, different model architecture, such as a deep network, as complex as that, or as simple as a regression. And then if you have knowledge and preference or bias, you can encode them into a constraint. And you have different workhorse drivers, algorithms that can be used to perform the optimization. And of course, you deal with data. And this kind of a way of talking about machine learning is already leading to some, hopefully, more clean and simpler way of creating machine learning. So again, let's see how to do that. I begin with a hyper simplified representation of a machine learning solution, which is shown in this function. In fact, even as simple as this, the function already shows you all the major ingredients that people need to address to come up with a machine learning solution. For example, the theta usually refers to the model architecture, including the parameters and also the topology of the model. And also inside theta, people already have some sense about the inference procedure. For example, in the RNN, you can actually have multiple ways of making the inference happening, as I'm going to show you in a second. So this is a space which we can set aside because it gives you kind of a scope where flexibility can be applied to make different choices without contaminating the other parts of the model. Other parts can stay constant, and by changing this, you already can achieve different effects. The next thing, of course, is the experience, which often is known as data, right? And again, you can leave everything constant, but change the data, you will get different outcomes, right? So you can drive basically different solutions just by getting data from the right domain or from the right customer to have the customization. Loss function is very important because that gives you a guidance in terms of how to determine the quality of the model when you are training them. And then, of course, constraints is a placeholder for many of the domain knowledge. Again, in any production and service-oriented companies, the subject matter experts are very important. Where are their contribution coming into? Well, it is coming into this part. And then, of course, in the end, you need to have the procedure of learning, which drives down or drives up a loss function. So map back to the running example problem in machine translation. You can see that this top box includes the data, and you can have a lot of flexibilities of choosing different data formats and different data contents. And then the model part, you have a space of design, and then the other part involves both algorithm and learning procedures and so forth. So now let's go back and hopefully take some time to look into each of the components one by one to see what are the options available in each of these dimensions. It's actually important to realize that the options are discrete, and you don't have to basically rewrite the whole code if you have a way to kind of systematically put all these options into a closet and pick them up when you need them. Architecture, of course, is the most interesting part, in this machine learning problem solution. For example, let's talk about possible options of the architecture, in the machine translation problem. One of the most popular and basic architecture people use for machine translation is to pick a language model. The language model is a formula that defines the likelihood or some kind of score of a input sentence. So in this case, say Y is the sentence, which is a list of tokens. You can write down, using a language model, the joint probability of that. But how to build a language model? Actually, there are multiple options. One of the most popular and standardized language model is known as the LSTM RNN, right? So that basically gives you one way of defining the language model. And if you are very up to date, you may know that nowadays people start to use transformers, which are multiple heads of self-attentions. And that could be plugged in without changing anything else, and you get a different solution. Okay, so another component of architecture is sometimes also needed. For example, you meant to deploy a machine translation solution into a working environment which has a certain context. For example, from which language you want to translate into or translate from. Say, I'm an English speaker, but I was given a German text. Well, that German text, where should we put them? Well, they are put them as a context. And then you need to build a conditional model to accommodate these kind of environments. Even in the different domains, say text generation from image, then the image can be functioned as an environment or as a context. And that means that your model has to be upgraded into a conditional model. And in that case, the previous main architect, which we used to model the language using either LSTM or transformer, now becomes a submodel. It's a module, basically, inside the bigger models, right? So it's now referred to as a decoder. The decoder is a placeholder for multiple choices that you want to choose. And then the conditioning context can be handled by another component. Let's call it an encoder. The encoder does the job of turning the inputs into some feature vectors. And how to do that? Do you want to write a code, or do you download a piece of algorithm from the open market? Well, you may be able to, but how to connect that part into the other part, which is a decoder, that actually already creates a challenge. So just to walk back to the much bigger overview, we now have a standardized encoder-decoder model in which the components can be chosen based on needs. But you also have potentially other architectural needs, such as a classifier, which is also often used in natural language application. They basically define the highest level of granularity in this so-called architecture graph. But you can walk down with a lot of more building blocks. For example, in the encoder-decoder model, you can have different options of encoder, decoder. You may also either embedder, because the text may conceal some of the latent space informations, which can be exposed when you properly embed them. Okay, and the classifier can also depend on an encoder to transform the input data. But also, you may need to build a feed-forward network as a classification layer to really allow nonlinear effects. And this feed-forward network can be built off different layers of local, functional properties, and they include maybe a convolution network or a dense network, and so on. And likewise, the encoder can come from all different, sub-architectures, such as using a RNN, a recurrent neural network, or a transformer, or a feed-forward network. And the RNN itself can be further divided into some attention models or some cells, such as LSTM. Right? So you can basically create a very big graph, which explicitly show you the dependencies and also the granularities of different building blocks. And that gives you a way of organizing a lot of the domain knowledge or expert knowledge of materials that you can use or knowledge you can use to create complex solutions. And with that, if they are made like Lego, then you actually could gain a lot of freedom and flexibility in creating compounded, more composite architectures. And here I show you a few examples. Right over there, you see the very standard canonical encoder-decoder model, but you can augment it with an attention model on top of. And you can also maybe upgrade it into a probabilistic variational encoder-decoder where some priors can be included. You can also set aside an external memory to allow a stronger inference and feedback between the encoders and the decoders. You can also even change the way the model is trained by replacing the maximum likelihood loss that people typically use with a adversarial loss. Nowadays, people are talking about GAN models and adversarial learning. And do you need to rewrite the whole thing? Well, with the material I'm going to present in a second, you will see that all you need to do is to just unplug a particular block known as the loss and replace with another loss. And then you have a new model, okay, trained on adversarial loss functions. You can, of course, also expand it into a multitask learning with multiple encoders and multiple decoders, and so on. You can have translations where models are aligned. So each of these new composition, if without a very systematic architect and building block and rule, really involves, if you write it from the scratch, it involves a lot of repetitious work. And also, the nice interface, the correctness are often very hard to be guaranteed. So now we saw architecture, and how about the other components like the loss and learning and the inference and the constraint? Well, I'm going to say a few words about the middle three because they are often highly intercorrelated, and it's better to see them together. So what does this? What option we have in the space of learning, inference, and loss? And here are some examples. Now give an architect we just used the encoder decoder, and let's say we want to try the simplest learning paradigm, which is known as the maximum likelihood estimation. Well, you can define the likelihood function out of the data x and y, and that basically can be again mathematically defined. But at the end of the day, you need to train the parameters in this model by driving toward a certain goal, which is known as the loss. So every learning procedure, say maximum likelihood procedure, correspond to a specific definition of the loss function. In this case, the loss is called cross-entropy loss. And every loss function usually suggests some type of, maybe one, maybe multiple types of inference procedure. In this case, one of the popular inference procedure is known as the teacher forcing decoding model, which basically is a iterative procedure which trains the decoder based on a partial transformation of the subsequence of the input using an encoder, which is functioning as a teacher to train the next iteration of the decoder, right? And you can also stick to switch to a fancier training procedure. For example, I mentioned adversarial learning these days are very, very popular. And how about try that? So what that amounts to? Well, it amounts to plug in another building block, which is known as the discriminator. The discriminator creates a new loss function which penalizes the decoder to be failing generating a sample looks like the real data. But if they can fool the discriminator and generate data like the real one in the training set, then we actually are rewarding the model, right? So this mechanism, again, can be very, very systematically driven by introducing the proper loss function, which also, of course, will be calling for a different inference procedure. In this case, for example, a Gabel softmax decoder. I'm not going to run into the math, or I'm going to say that this can be pre-implemented and plug into it if you need it. You can go as far as the latest kind of option of training the same model using something known as a reinforcement learning. The reinforcement learning is directly sometimes optimizing the stuff that you want to optimize. For example, one of the measure that people use in qualifying the natural language generation. After all, your machine translation is generating natural language, right, from one language to the other so that it's readable by human. And the quality of that, in addition to accuracy, is about the readability and the naturalness of the sentence. That's measured by BLEU score, right? So how to directly, optimize over a good or better BLEU score, on the output of the decoder? Well, this reinforcement learning algorithm allows you to do that. it basically asks you to generate samples, okay, of from the decoder, and compare the samples with the training example, and measure the differences of their Bruce score, and then create a reward. The reward can be positive and negative, and then accordingly they will augment the decoder model iteratively, right? So that loss is known as the policy grading loss, and that inference algorithm is, in fact, there are a couple of different algorithms. What I just mentioned is called the sampling decoding. Again, this can be pre-implemented and put aside for you to use. So if you go down the list, you actually can, I just gave you 3 examples of the learning, MLE, adversarial, and reinforcement learning. The truth is that you can go even the list longer. There are a lot of combinations of the above, and also new instances which are less practiced because of their complexity in mathematics, or because you just don't find it in the so-called algorithm marketplace, right? And for all this loss and the inference, I also gave you quite a few examples already. Now let's look at a constraint. Okay, just for the sake of completeness, constraint is actually a very important thing that has been underplayed, in how should I say, maybe the academic-minded research, because in the academic-minded research in machine learning and AI, people worry more about the mathematical elegance, or maybe the benchmark performance. I tell you that on these 2 things, the constraints isn't giving you a lot of advantage. First of all, adding constraint will make the math more hairy. Therefore, it is harder for you to prove any results. Therefore, people walk it away. And also, if you only worry about the test score in cargo computation in image nets, you don't get better score either, because these constraints will weaken your model in terms of performance. Okay? But in practice, when you are solving a real-world industrial problem or medical problem where you don't even know the test data to be the same, whether they're the same or different from your training data, and you are not basically given the environment of a benchmark standardized environment, constraints can give you a lot of advantage in beating a canonical model, because they can navigate you away from some risk area, such as a rule being violated and so forth. For example, your temperature may just go too high in your cooler, so that it causes an accident, even though mathematically the high temperature gives you a good outcome, right? But how to include constraints, it's actually mathematically quite non-trivial. And here there are some simpler constraints, such as goal sparsity and goal normality and so forth, which people know how to do it. And there are more complex ones, such as rule-based constraints. That's actually the kind of constraints we run into most often in our own experience with the industry. For example, when you do machine translation, and you want to also at the same time make some product recommendation, and in order to make a good product recommendation, you need to understand whether this individual is in good mood or not. That means sentiment analysis become useful, right? Sentiment analysis usually can be derived from the whole text, but sometimes there are some catch which you want to know. For example, in this sentence, food was good, but the service was disappointing. This but actually sometimes leads to a half sentence that dominates the whole thing, no matter what you say in the beginning, right? If you knew that, you actually wouldn't be bothered by the whole sentence. You are only going to pay attention to the later half. And that's a rule not useful to know, because a naive model may compute an average of the whole thing and give you a wrong estimation of the sentiment. Maybe the food is good, therefore that guy is happy, but the truth is that he may be not. Right? And this can be actually formulated using a logical function, and which produce the right truth value based on that kind of rule. Likewise, if you want to generate, for example, in fashion applications, you want to put different fashions on a person's body, and for a virtual try-on, for example. And that's also a very difficult task. You need to do the right segmentation of the input picture on body parts, and then you put them together with all these clothes on. And sometimes when you put them together, just by optimizing some kind of canonical loss function, you may put the head under the trunk, or you may swap the limbs and that. That's possible, because all these parts out of the context may actually drive your overall likelihood in weird ways. You will see very, very strange gestures and the body configurations, which you don't want to show to the people. But if you know that as a rule, we know how human body look like, how a normal pose or how a normal gesture should put all these body parts in different places, then you are in safe zone. You don't violate that, right? And how to encode all these kind of knowledges, right? So these structured knowledge, in my opinion, are very important in battlefield machine learning. And again, they can be built into building blocks. And here I give you some ideas. For example, in this particular knowledge called the variational knowledge representation regularization, you can basically specifically put the constraint function into the loss function, together with the loss function, into a new, together with the target model under the new loss function. And in here, we can introduce a kind of an auxiliary helper in this case, which we call a teacher. That teacher actually is technically called a variational distribution, but in practice, they play the role of being the one-time teacher to drag the model to be trained, which we call student, to a better direction. And it is a pretty complicated mathematical procedure which involves the following iteration. First of all, the teacher needs to combine the knowledge from the constraint with the current status of the students. And then the students will be learning from this teacher in the next time point and gets improved and so forth. Again, implementing this procedure based on different model architecture and based on different type of data can entail thousands of lines of code. And again, what we do is to put them into one of the blocks out there. So with that, you can see, the machine learning, this under the umbrella of the word machine learning, if you view them in an unstructured way, you'll see these whole pages of equations. But if you follow the first principle, as I just said, it is possible. In fact, it should be the case that we view machine learning in this highly systematic way. And then you can imagine machine learning, as a training camp. It's very much like a university where you send students, an untrained model. I sometimes often call the untrained model to be an empty brain. It's like a student. And then you go to the university. The university has all different teaching materials, like the textbook, they are the data. And they have different classes for different tasks. And they have different teachers using different methods to teach you and so forth. And these are basically now listed like this, okay, using a very, very systematic kind of curriculum in a sense that you can choose from, right? And that holistic view actually gives you a lot of kind of advantage or clarity in understanding the dependencies and also the pipeline that you want to assemble to achieve a very, very explicit effects. For example, the maximum likelihood loss learning procedure corresponds to certain specific loss functions, in this case, the cross entropy. But the reinforcement learning learning procedure corresponds to multiple alternative loss functions. It could be the policy gradient loss. It could also be the policy gradient loss plus a baseline and so forth. And then each learning procedure can be solved by one or multiple inference protocols. And here the dependency can be made very clearly. And of course, architecture of different kinds can enjoy different choices of the inference procedure, different choices of the learning paradigm, and so forth. So the combination of all these components that you need to decide to create a solution can be nearly infinite. Okay, and that's why machine learning are known as so complicated. Even a seasoned professor sometimes will have a hard time in navigating the entire space. At least the way I navigate is to form this mental picture in my brain already, and then I don't have to remember all the terminal solution. I remember all these building blocks, and I assemble them, okay, based on what I need to solve. But again, it takes still a lot of experiences. It tells you it requires to remember all these components and what exactly they do not do. And for a standard developer, who have a limited lifespan in their time to learn, and they have to make a value and contribute to the work. I guess some better tools are needed other than just send them back to the grad school and take another PhD and so forth, right? So that's why, a tool, for, operationalize, this chart, make them, a real kind of Lego place that people can play is becoming a very, very, important, in my opinion, if not even lucrative business. The approach we took is to start define uniform interface so that with different choices of the architectures and with different choices of the inference procedures, for example, you don't have to go to all different places and dealing with different coding convention, different coding language, or even different traditions of writing the same thing and so forth. The single interface, hopefully graphically, if not programmatically, can give you, a one-shop place to get all this available. And then when you need to deal with the more nuanced choices or lower granularity choices of loss functions and the constraints and so forth, you can treat them as libraries of subroutines so that you can call them, hopefully, very easily without even necessarily knowing how mathematically they work and how to write it up. So that's basically our kind of a beginning message of the composable machine learning. It meant to really systemize the general machine learning technology as a science into a more engineering-oriented standardized building blocks. You can view them as the Legos, or if you are more kind of romantic, you can view them as the musical notes people use to compose. And then those rules and those constraints can be viewed as chords and rhythms, which are kind of give you, some constraints and some limitations when you are making the compositioning happen. And then with that, you can build a programming language at an intermediate or higher level on top of it, rather than directly dealing with equations. In fact, if you look at TensorFlow and Python, what they do is to deal with the raw math. Okay, yeah, they don't need you to derive, for example, the gradient of an equation, which is great. But you still need to put that gradient, which are automatically computed, into the right place. And you need to actually write down this whole network, which I think is a pretty challenging and exciting job. But unfortunately, not many people can do it. Okay, it's a very, very low-level language, powerful but difficult. What we want to do is to using this composable view of machine learning to give you a more flexible and a wider range of composability, coming above the low level, and give you the choice of making different solutions. And the future vision toward this is hopefully we can even be graphical and literally, drag and play all these components and build something. But it's not happening yet. I mean, it's actually something we are doing in the company. Okay, so let's dive into what we actually operationalize it. This program called Texar is a initial foray into the vision I just presented, and currently it is mainly focusing on a intersection of the grander machine learning, universal overview with the field of natural language processing and computer vision. It's quite big already, but it's not the totality. And I'm going to use, again, the machine translation example to show you how we operationalize those composable building blocks and how to compose. Just to recall this equation, and we already dissect this equation into a architecture diagram, and we said that this is how an experienced machine learning researcher remember them, basically, in their human brain. But that diagram is too much for a computer to remember, honestly. It's too, how should I say, too ad hoc. How about this? In a computer's brain, I think all they remember are, stacks, stacks of categories and lists and libraries and so forth. So we turn this one into this one in the first place. That's basically the building blocks in Texar. And we've got a big catalog, if you want to really index them and read them. And this catalog describes, in the order of a few, I think quite a few hundred, if not thousands, of little components already, which hopefully covers a pretty big space of all you need in doing natural language and general machine learning composition. It's very, very modularized. Okay, every piece is encapsulated with as a subroutine with proper APIs, and it is very versatile. For different text format, different tasks, and again, different, of course, and ideas for algorithm inference and learning. And it's also extensible. If people want to contribute new functions, he only needs to follow basically the design of the I/O, and everything encapsulated can be created based on the developer's own style and needs. So now let's see an example of how to program with Texar on a non-trivial applications like this one. Okay, machine translation. We begin from data, and in fact, as you can probably appreciate, this whole thing is not it's not solvable quite trivially by a piece of downloadable code from some places that gives you a text alignment, say, between two languages. Because you need to be receptive of different forms of training data, depending on which company or which client you work with. And also, you need to turn the outcome into different languages, depending on which country or which place you want to deploy your solution. And it becomes subroutine in many other bigger applications. For example, in the medical report generation, the translation part is actually just the last module in this whole pipeline, because before that, you need to first generate the source language, and then depending on which hospital and which country you deploy, you do the translation part. So let's see what are the components or the modules needed for even completing this simple task known as machine translation. You are given this data, right, which are aligned, between source and targets, and you need to create a vocabulary book, which hopefully can be easy. And what it takes, in our programming environment, to complete the model or the data preparation, are basically done by these two sentences, two lines of code. Okay, you call a parallel text data function, which start to align you the text. And then you also call the data iterator, which helps you to clean up the data, removing stopping words maybe, and maybe truncating some text into a standard length and so forth. You get the data basically ready to play. And then you start to build the architect and also the inference. That's where things become interesting, right? Your raw text, before they can be modeled into a encoder or decoder type of translational environment, you need to find the proper embedding first. Because as I said, a lot of the semantic information are concealed from the raw text at the surface form. If you do backward word type of modeling or do just the direct word level language modeling, it doesn't really work very well. So embedding means that you need to employ some kind of feature generation function to turn the words into some vectors, which includes the predecessor context and the later context, or even maybe the global context of the whole article. And that can be achieved by calling the proper embedding function. And then the output of that proper embedding function gets consumed by the encoder. And the encoder then encodes them into the next level of features. And then you need to build a decoder, which is really the meat, the nexus of this whole solution. Again, as I mentioned, you need to choose a architecture first, and in this case, we choose a canonical one. Let's say just the attention RNN decoder. And again, you have different ways of training it. Usually, people begin by a very, very classical and elegant maximum likelihood training. And as I mentioned before, in this category, your loss function is known as the cross entropy loss, which needs to be computed. And you need to also employ a particular inference algorithm, in this case, known as the teacher forcing decoder. And so these are basically already annotated in here. And what it takes is to basically load the decoder, identify decoder, load the data, and then here you basically are calling the proper loss function, and then this procedure is kicked to start. Right? So it's very simple. This literally is the program that you need to write to complete the machine learning machine translation function I just mentioned. And this is just a play, telling you, how trivial it can be. If you download the Texar, you can actually play it on yourself. We usually need to write some config file to tell people where to find the file, how do you want to keep the sentence length, and how many tokens you need, and so forth. And then after the config files are produced, you put them into the program and you run it. And the training, can basically be taken care of, by the computing engine, which, in fact, we have our, if you want to really train fast, you can also use the parallel training procedures and other, computational enhancement technique, which I'm going to speak a little bit later. This is also machine learning. But at the end of the day, you get a trained model like this very quickly. And then to text them, same thing. You just write another config file to give them a new file of source language, and then they give you the translation. In this case, some examples of English to German translations. So I welcome you to play up these kind of algorithms. At least it gives you some initial starting point of making a serious machine translation program already, just by these few lines of code. I believe the example code is already there that you can directly play with. But this is just a start. In fact, more sophisticated and adventurous developers are not satisfied with just one way of training the model. The same model, just like the same student going to the same school, can use different curriculums and make them, biased or specialized, on things in different ways, right? For example, here, how about try something different? We heard about adversarial learning already. What that can be, can achieve, and maybe even reinforcement learning, right? Again, we have this library that pre-built many of the components already. Therefore, changing paradigms and experimenting with different procedures basically amounts to writing a few alternative lines of code. So in this case, I will just give you a side-by-side comparison. For example, we saw this a few lines, I think 2 or 3 lines of code, which correspond to the maximum likelihood training. The essence is that you need to define the loss function. You need to also identify the right decoder, which is the right algorithm, right? And that's the 2 things you need to change if you use a different training program. Say in this case, we know we like a adversarial training. Therefore, the loss function becomes a binary, adversarial loss. It's actually the adversarial loss, due to a discriminator, but you don't need to understand what is the discriminator. All you need to do is to call the loss function. And then they will need you to call the right inference procedure, in this case, a Gabel softmax decoder. Of course, if you say, I don't really know, even for a reinforcement learning, what should be the right loss and what should be the inference, well, then you need to read the catalog, because it assumes you to at least know where or what thing you want to use, but you don't have to create that. But if you are really saying, do I have a auto ML that made everything for me already, I don't need to do anything, well, then you just download the program and it's actually pre-made. If you don't want to do any flexibility, that's also possible, but I don't recommend that, because the whole point of Texar is to allow you experiment, a lot of different options without bothering yourself, coding up all the details. Just for fun, a third choice, reinforcement learning, which is really fancy and quite non-trivial to implement. And here, again, you need to choose now a slightly more complicated procedure because it's not only involving choosing the right loss function. In this case, it's the rewards based on the sample. But also, the rewards are defined by per sample. Therefore, you need to have this iteration happening so that the rewards can go back to the decoder and generate the next different samples to hopefully trigger a better rewards. So it's not a one pass of all data. It's not batch learning anymore. It's more becoming incremental learning. And therefore, little micro here is needed for you to experiment with. But you don't have to code your decoder from scratch. You can call something called a random sample decoder, and you get things done. Right? So you can imagine, with literally a few lines of code, you already are in the space of anywhere from the most classical to the most state-of-the-art, advanced, decoding procedure, and maybe even different architectures. So that really makes explorations and experiment, even developments, a lot easier, in my opinion. So the whole point is to, in the future, allowing plug and play, plug in and plug out models and modules, then you can get all different outcomes. Okay, so that's really where the Texar is trying to offer. I bet many of you already have a lot of questions already. In fact, we have time for questions either now or after. Which one do you prefer? I already prepared some of the questions you may want to ask. Right? For example, people may be curious about, hey, we've got TensorFlow and PyTorch. I kind of said a little bit already what's the difference, but here I just want to revisit this point. Well, they are different, but they are highly, highly dependent. In Texar, we choose not to build our own low-level language because there are very good ones out there already. Why not just use it, right? So TensorFlow and PyTorch are the foundation of our program at the low level. They become the computing engine, okay, to enable, for example, gradient computation, enable some of the graph computing and so forth. We don't do that, from scratch. But we support both because TensorFlow and PyTorch really have competing non-overlapping advantages. And when we are deciding which one to use, we eventually converge to using both. Therefore, we end up with two different versions of the Texar. One is the Texar TensorFlow, the other is the Texar PyTorch. And you can see, in addition to this common advantage of having very comprehensive machine learning functionality at all different granularity, if it's based on TF, then you have slightly weaker programmability, but you have a lot of powerful low-level computing support, like the serving and like the mobile support, and maybe parallelizations become a little bit easier. But if you enjoy more flexible programmability and easier debugging and editing, if, for example, you want to contribute more components into Texar, then PyTorch is a very, very good tool to begin with. So that's one kind of a clarification of our position against TensorFlow and PyTorch. It is complementary. And therefore, when the library of TensorFlow and PyTorch grows, we grow as well, automatically on top of that. The other question people had in our online blog was that, language models has been quite popular these days. We heard like the BERT model, right, in many places, and they give you state-of-the-art performance, on certain embedding functions, maybe down the road more functions. What's the position of Texar versus that? Well, again, we want to be a good friend of that. For example, if you really like a particular BERT model to embed your raw data, you can just call it as a subroutine. Okay, it can be a pre-trained. In fact, one of the biggest value I found from BERT is that they have a lot of pre-trained models. Why? Because Google had a lot of computing machinery and a lot of big data. Therefore, they can really train a model like no one else. We don't have the data and the machine. Therefore, even though we have a placeholder of a BERT model, we cannot get the parameter right. So downloading a pre-trained model and use it directly for embedding is great. And we can do that. But if you come from another big company with all the good data and machine, you can also load an empty model and train yourself by calling slightly a different function. That's possible, also inside Texar. And not only embedding is supported, you can do many other things like classification or sequential prediction using one function alone or using several BERT functions in Composite. What I'm trying to say is that we make BERT a component itself inside our family, but of course we have more components outside of the BERT functions. So that's giving you kind of a bigger picture of where we are, right? So these are the tools nowadays people are using all the time. And out there, you see the PyTorch and TensorFlow, which are highly modular, composable, low-level languages, which are very powerful. But it takes a lot of domain knowledge and specialty to build applications on top of them or from them. And out there, on the upper left corner, you have what I call libraries of either templates or programs which are pre-made. In a sense, it's pre-made, therefore very hard to change it, very hard to interplay between them, and not allowed to extend them, right? So we are kind of in here. It's having a wide coverage of different granularities in terms of functionality and also programmability. Therefore, you become more flexible, in building different tools the way you want. So this is just a text summary of what I just said. I'm going to pass. And of course, I'm here to, first of all, advocate the concept of decomposable machine learning. And of course, I'm also very interested in promoting the usage of Texar. By the way, Texar is an open source, freely available thing that you should feel free to download and play. But you may ask, am I honest with myself? Does my company use it ourselves? Well, we do. We actually use Texar as one of our major development tools for a number of advanced applications. And these applications, some will be also made available as a public service. For example, Forte is one of these toolboxes, which are, I'm going to say more words about that. It's actually a very powerful thing where, for example, the machine translation tool and also, say, the medical image report generation tool are already half made as a scaffold. And then you can make all different choices of the building blocks to turn different features up and off, because your training environment and data may be different, but you don't want to bother even building the scaffold because interoperation between programs sometimes can be very non-trivial. We also use it for generating a number of production level applications such as the X-ray report generation tools. We also use it to build chatbots, for foreign languages. Which are actually in the stage of testing already. So just take a look about how, for example, this X-ray reporter writer can be made, right? That's again, as I said, is a very non-trivial, major, undertaking, going way beyond just labeling an image based on some deep network. You begin by processing the raw data, such as image, but also text notes and other information, life vitals and others. And you need to go through this long pipeline of feature extraction, maybe local signal recognition using classification or ROI bounding boxes or attentions and so forth. And then you need to generate alignments between the image components and the text and so forth. And then after that, you're going to employ some kind of text generator so that they can consume all this raw information and start describing the phenomenon in a humanly readable way, in fact, in a quite professional way, so that they can kind of save doctors' time in writing all these materials. And then if, of course, here, we choose to use the English as kind of foundational language for, enabling this function. But your readers may be in Japan or in China or in Europe, then you need to do a machine translation to translate. So this whole thing obviously has a lot of components, right? And that's actually where we found Texar to be really powerful, because we don't really roll out a monolithic program which is a single black box. We actually literally built our tool in this way so that when we are deploying the tool to a different country, for example, we only need to replace this part. When we have information, say, only from image, but not click notes, then we turn off one of the modules. Okay. So you can imagine, we're not a research lab, we have a company needing to make profit, we have to amortize the cost and enable reproducibility and repeatability, right? So that's where we can save cost and save time. And I hope, down the road, if you have a chance to play with this, you may find the same advantage. I'm going to skip that. This is just a demo about our very fancy, kind of a text generation function, a report generation function from the X-ray. I don't think, it's in fact, it's generated in Chinese, so you can see all these functions encapsulated. All right, so this is where you can get, the supports, including the source, the code, and templates, examples, tutorials, and also a very detailed text report, which actually won the nomination for best paper in this year's ACL conference. So this whole thing is available on GitHub. Okay. And please also, feel free to write to, the website myself about your feedbacks and needs. So I'm about to run out of time. I'm going to just give you some kind of an overview about the bigger offering, supporting or surrounding the Texar, right? What I just mentioned is about creating an AI application, but how to really, it's already becoming, hopefully with the help of Texar, it's already becoming kind of systematic and standardized, maybe even repeatable already, but how to scale up and scale out. For example, you want to train a particular language model based on really large data using a really large model. Well, computing becomes bottleneck. And sometimes you need to use pipelines. And therefore, you need to figure out the interoperability between different components. And sometimes you are in a company, you have multiple users building different production lines. How to share computing resources? Well, usually developers don't worry about this, but the system admin and maybe other IT leaders worry about that. Do they give the machine hall to you, or I need to do a lottery or do some scheduling, right? In fact, all these are part of the AI developments. Many developers just don't want to dive into. They will assume that these are all taken care of by their neighbors or by their friends or by their back-end team. But now we are looking the whole problem as a corporate level, that it's becoming your problem, not others' problem, right? So in here, we have a couple of toolboxes. Forte, for example, is the inter-task interfacing application templates, the library of that. If you want to work on different applications, you can hopefully get a template already pre-made from there. Aaron is I would say, an automatic distributed machine learning engine, which allow you to train on big model, on big data. And then Asper is a scheduler to automatically, elastically give you resources. So I will say a few words for each of them. This is Forte. Basically, it gives you, pre-made scaffold that you can fill in the flash to make it a body, okay? And that includes here, for example, the raw data processing. You have zillions of ways of processing your raw data. And hopefully in this library, you already find enough for your own needs. Translations, analytics, for example, you want to do sentiment analysis. You want to maybe classify or cluster populations or styles inside the text, right? So you can actually find tools out of there. And then, of course, if you want to write and compose text, you can also find scaffolds, pre-trained models, to satisfy your need, meaning that you can train based on your own data. Of course, we could consider offer trained data already, but honestly, we're not a data company, therefore our training materials may be not adequate. But anyway, that's a potential people can find useful. On Arion, on the high-speed, parallel computing engine, people very often underestimate the importance and the value of that. CPU, GPU machines are nowadays very, very expensive, in fact. If you are not made good use of that, you end up losing a lot of money. In fact, we cannot afford very often to buy Amazon time or machines just to train all the models. And the real difficulty is because for different models, to to parallelize their training is not trivial. Why? Because they require different methods to parallelize. Sometimes a parameter server style kind of master-slave parallelization is good enough. Sometimes people use all reduce coming from Google, but sometimes you need to do more sophisticated broadcast, such as a peer-to-peer broadcast for a more kind of elegant distribution of the task and so forth. Implementing all this at the lower system level, not using Python anymore, using C, is very challenging, right? So Aaron is basically such a system which gives you all these choices. Either you made it or they determine it by themselves automatically and give you the scalable computing results. And here are some numbers that you can see. It's well, there are not a lot of reference point for us to compare with. There isn't really a product of our nature. But for certain instances, say a particular model parallelly trained on a particular system, we did find some numbers. For example, we are roughly on par or slightly faster than the state-of-the-art parallax. And then we are 2 or 5 times faster than TensorFlow and even more faster than the Harvard. These are just the standard benchmarks. But don't read too much out of the numbers. I guess the point is that there is a place which you can make choices of different scheduling and parallelization procedures automatically to train a large number of different models. Very rarely your entire solution use only one model. And that's actually the true advantages in here. The other part is expert. Again, a few words other than what I just said. In order to really better use your limited resource, you better schedule the resource not as a fixed amount of kind of asset to a particular user. Very often say, hey, I'm going to lock the machine away for the next 72 hours because of the deadline. But the truth is that between these 72 hours, you may be on and off, and your workload are fluctuating. And if the system is smart enough, your resource should be actually distributed to other places, right, to carry more work. And this is done by expert automatically. So we are really trying to manage computing resource at a corporate level. And so that's, again, could support the Texas adoption in a big production environment. So last but not least, there are additional things needed for AI production. All I said earlier was about the training and maybe creating the prototype of solutions, but at the end, how to wrap it and put it into the marketplace and put it into the client's infrastructure. Well, composability may be useful because the UI could simplify the learning curve or the time needed to understand this set of resource. And also, how to manage programs writing in different languages. We already see, programs writing in Python, in Java, in C, and all that. And you also need to have a database, in Spark that is needed to store, the information. How do they come together? Do you build a different infrastructure, one for each, or they can live in a single unified environment? Well, Fugue is actually helping that kind of interoperability. And finally, of course, the infrastructure management in the form of a containerization, virtualization is also what we offer as a whole system. So maybe I should sum up here. What we are doing in my own research and also in my entrepreneur world inside Petuum, we really are aspiring to build a system called Petuum OS, where we can really turn the production and the practice of artificial intelligence into a civil engineering-like practice, where you are adopting universal and standard rules to do this kind of Lego play. Okay, pick and choose and build. And hopefully this approach can be industrial agnostic and really can lead to complex solutions without tears. I think that's where I want to wrap up. I want to just share with you the mission that our company is trying to push forward industrializing AI and transforming all industries into the AI era. And this vision, as mentioned in the introduction, was acknowledged by the World Economic Forum Tech Pioneer Award last year. So with that, I want to end here. But last but not least, I do want to stress that I'm not only a presenter of this piece of technical material, but also I'm an advocate of my company in terms of talent acquisition. I really want to invite all interested people to apply, working with us to together push forward this vision. With that, I want to conclude and thank you for your attention, and I'm ready to take some questions as well.